Hey everyone, this is Amritansh, and with me, as always, is Tamal Acharya. Hey Tamal, how are you?
Hey, hey, I'm doing good. How about you?
I'm good, I'm good. Thanks for asking. So guys, I think now we are almost reaching at our end, and one more video will come out. This is our ninth video. And today we are going to look into some of the novel architectures. We are trying to understand what has happened in this field of AI research, AGI research particularly, and what are the some of the novel architectures we could have please have a look at. And that's how our discussion is kind of poised today. Okay.
Yep.
And we have already released 8 videos, and we will really love that if you guys can go through them, if anyone has missed any of the videos. Okay, so I think we can go and start talking about AGI. Now, again, I don't think so I need to introduce any of this. This is very much known and which very we understand. And even if some research, it might look like some research advances have happened right now, I could assure you that the seeds were like put like 20, 30 years back, but it was not possible for researchers to implement those algorithms with the full efficiency back then. But now it's totally possible. Now reduction in storage costs in last 2 decades, which brought around the concept of big data. Like we can store like exabytes of data really easily.
Mm.
Computing resources, right? GPUs have changed the game, which were initially designed particularly for gaming and still are relevant for gaming. But I think one of the biggest markets is definitely the data center ones, especially around AI, where you are training these massive neural networks, and to parallelize them at a scale, you require all these humongous amount of CUDA codes in each card, right? And of course, you can call it, I will also call it like the use of social media, internet, all of that also comes. So a combination of data sets, algorithms, and computing advances have caused an inflection point in our history. And right now, what we are seeing is humongous push for various novel architectures in order to achieve or kind of keep moving towards artificial general intelligence. A very famous researcher called Rodney Brooks, he was MIT robotist, and he fundamentally said that it might not even arrive until 2300. So you have to understand he is taking a very big time frame, and he does mention something very important here, that we do understand what is the true promise and dangers of AI. And most of it, whatever we read in any headlines in newspapers or any in mass media, is not really the truth that we are really working with. Okay, you have to understand it very well that that's not the truth. Okay, very rarely like that is like even close to what is happening
Mm.
in the research. Okay, and of course we are thinking whenever I say AGI, we are thinking general purpose nature of intelligence, and we are talking a holistic and integrated viewpoint of intelligence. Like we are considering different sectors, and we are not only just constraining ourselves to computer vision, NLP, or sound processing. Okay, and of course, we want to believe that our time has come to build that AI that is comparable to human intelligence, or which is much, much closer to human intelligence. Okay, and of course, like this is like our AGI definition is much closer to AI definitions, but uh, today's mainstream AI research, I think, is very domain specific and problem specific.
Mm.
Because see, guys, there is still no unified platform or unified architecture which could solve the problem of AGI. And it is similar to notions like strong AI, human level AI, complete AI, thinking machine, or cognitive computing, and some other keywords thrown around. Okay. So fundamentally, Dr. Pei Wong has basically described that AGI research has the science part theory and engineering, that is your technique aspect, and complete AGI work
Mm.
would normally include a theory of intelligence, formal model of this theory, and the computational implementation of the model. Because without that, how would you even implement all this? So all of this is required in modern day AGI research, and we have like this idea. But I think I would like to ask Tamal and ask him that like what
Yes.
kind of like different projects that we are having around AGI, and what kind of similarities or what kind of overall properties does he sees across
Mm.
them.
Yes, that's a very good question. And thank you for giving the introduction to AGI and setting the stage. Now, before we move into the novel architecture, which will come a bit later in the slides, we like to what I like to introduce here is some of the uh, some of the criteria, or you can say some of the headers under which the entire projects can be categorized. Now, this is very important. You need to understand these things. I mean, how people are approaching. It's not one approach. It's like people are approaching from various points of view, because everything comes from our human brain. Now, we are understanding human brain as and when neuroscience, all these researches are happening. We are trying to see how they can be um, converted into something of a novel architecture, or how we can implement, I mean, replicate a certain portion of the brain and then understand how it is functioning and then do something on that. It's like that. It's not a complete picture. We haven't reached that stage yet, but there are parts, I mean, you can say. Now, the entire AGI projects can be categorized into few stuffs, like there are 5 broad categories which Dr. Pei Yuan has introduced. Like, we can approach AGI from the structural point of view. Like, this is the, say, the rationale behind is that intelligence is produced by human brain. Now, to build an intelligent computer means to simulate the structure of the brain as faithfully as possible. Now, this has been done quite a few times. Like, all these supercomputers that are being developed. So, University of Berkeley has done something similar. Like, there are researchers in Japan and other countries who has successfully produced, replicated certain, I mean, aspects of the human brain, like an activity. Now, this is coming from the neuroscience point of view. Example, HTM, which we'll kind of discuss later. Then few of the papers from Vicarious also introduces the very aspect, like how do you approach the AGI from a human brain point of view, from neuroscience point of view, from the biological aspect. Now, then there is something called behavior, like human behavior, like intelligence displayed in how the human beings behave. Like, the goal should be to make a computer as behave as exactly like a human as possible. Now, background is psychology, linguistics. Now, this is one more aspects, like the Turing test, the cognitive model by Josh Annenbaum. So he has done extensive research on these things. Now, you can go through his papers. Like, so his approach to AGI is more from the brain point of view, like the behavioral aspects. Now, going forward, now capability. Now, the intelligence is evaluated by problem solving capability. Now, intelligent systems should be able to solve certain practical problem that is kindly solvable by humans only. Now, this is a test, you can say. Like, we humans solve quite a varieties of tasks every day. Now, a system to do just that, meaning that system should have some capability, some functionality, through which it can tackle those kind of things. Examples are AlphaGo, expert systems. So now AlphaGo, so there now it has evolved to quite a few things. Now Mu0 is there, and now AlphaZero is there. Now they are mainly from the capability point of view, like AlphaGo just defeated the Go player. So this is capability, how you are capable of solving a certain type of problem. Now it has understood that game, then it has beaten a human champion, and then it has produced, okay, I can understand that there's a problem in front of me to understand the game. It has understood, then it defeated someone. Now, then from the function point of view, now intelligence is associated with the collection of cognitive functionalities such as perception, reasoning, learning, acting, problem solving, communicating. Now, goal is to reproduce these functions. Now, there are, so this is from the computer science point of view. Now, there are mainstream AI textbooks which introduce these kind of things. Now, there is SOAR architecture, which will come later. Like, this is one of the projects which kind of is, getting traction, like from the functional point of view. Now, we think it's not one, it's not like only capability will solve that thing, only function will solve that. So it's like a combination. You have to combine all these things. Now we'll come to that later, like going forward. Yeah. Now the last thing is the principle point of view. Now, intelligence is a form of rationality and optimality, and intelligent systems should always do the right thing according to certain general principles. Now, here comes certain assumptions, certain principles through which we also act, we function based on those. Now, there's AIXI, which is from Marcus Sutter, which is one of the very famous architectures on universal intelligence. And then there's NARS. Now, all these structures, all these things, like you can say that we have to combine all of them to get one system which will be capable of doing of anything. Like, so if you combine all these things, basically get a rough idea of how the human brain works. Now, if you combine all these things, now our AGI also will have to do that. Now, from top to bottom. So now these categories was done by Dr. Peiyuan's research. Now he has described few things like, so these correspond to descriptions of human intelligence is more and more general level to reproduce the description in computer systems. Now, this is how you should replicate. Different descriptions have different granularity and scope. The objectives are related, but still very different. Yes, you are coming from different points of view. Like, so now then you have to reach a certain goal. Now, when you combine all these things, so you approach, so there is a point and you are approaching to various roads, you can say. Now, when you do that, we'll get there. Now, so there are researches going on, but it's like, as I said, you have to combine all these things to get the entire picture. Yes. Now, going forward, now there are three techniques, broad techniques. So those are like structures. Then this is like techniques. So there is hybrid technique to develop individual functions first using defined theories and techniques, then connect them all together. So it is compatibility of the theories and techniques. So it is like the practical versus theory. Like we study something like in college days. So there is theoretically you can study many things, but when you try to implement that practically, you will face lots of challenges. Now, this is how it is. We have faced that. Then we say, no, practically, if you want to implement something, there are some certain assumptions, certain caveats which you have to assume, which you have to take into account before you implement certain things. Now, that is one thing, hybrid approach. The second is integrated approach. To design an architecture first, then design its modules using various techniques. Now, you have an architecture, then when you have the architecture, it is like a software development. You have a blueprint. Then individual modules are being developed. Then they are connected. Now, this is integrated approach. Then there's something called unified approach. Now, unified approach is using a single technique to start from a core system, then extend and augment it incrementally. Like you start from something, then you keep on adding. That's this unified approach. Now, same as before, the same question. Does one approach will work? I don't think so. All the three should be combined to get, because this is how we human brain is made up. So we do take sometimes hybrid approach, sometimes integrated approach, sometimes unified approach based on what we are trying to solve. Now, if you have to combine, all three have to be there so that it understands, the system understands, or the AGI agent understands that what is the problem, based on the problems, we should take the approach. So this is how. Now, these are the three broad categories. Now, coming to the AGI projects. Now, again, Dr. Peiyuan laid down certain criteria on which we should assume the all these projects falls under. Now, see, there are lots of things happening. Now, which one we should call AGI project, which one is a narrow AI? Like, this is very important to discriminate here. Now, here are certain criteria which Dr. Peiyuan laid down, based on which we can tell that these are, we can take these as a AGI projects. Now, it is clearly the first and most important thing. It is clearly oriented to AGI. IBM's Watson is not AGI. Google's AlphaGo is not AGI. They are solving certain problems. It's a platform to solve certain things. It's not a true AGI. Second, it is very active. It should be active. It is not that something has happened 50 years back and then it has stopped. Which means it has stopped means it cannot go forward. We should not be taking those projects into account. Yes, there are certain things. Sometimes it can happen that some old stuff from the shelf, when we look at, we say that, okay, let's try this now. It was not done there because of some limitations due to which it was stopped. But those are very rare. So it should be active, and it has ample publications on technical details. Like there are many recent AGI projects which are not included, like Gödel and so this autonomous paper by LeCun that are used to represent various deep learning projects towards AGI. Now it should have ample publications. Now Gödel has paper, LeCun has produced this famous paper, which is kind of, people are saying it's a game changer because that is one way of thinking. Now, it should have ample publication. The reason being, if we don't know about it, what is going on, then how will you know that it has, it is actually going to contribute something in the future? Now that it should have publication so that we are made aware, everyone is made aware, everyone is aware of some certain things, though technical. So these are the three criteria. Now, if we move on to the next slide, see, these are all the projects, AGI projects that are currently being developed or being researched upon by various teams. Few of the notable ones here are AIXI by Marcus Hutter's team, Gato from DeepMind, HTM from Numenta. Then there's MicroSci, which is very good. I mean, it's on synthetic intelligence. There is OpenCork from Ben Goerzel. Then there's SWORD, the SWORD architecture, which I just said a few lines there. Now, all these things are kind of taking into consideration those three categories. I mean, all the categories, we'll come to that later. And then all the three, the criterias on which you can kind of segregate these projects. Now, if you move on, you can go through these details. We'll share the link. I mean, it's basically there in Dr. Pei Yuang's personal website. We'll share the link. We can go through and read in detail. He has given a very good description of everything. Now, remember the 5 goals or the structures we introduced earlier and the 3 techniques we introduced. Now, if you see this matrix, now all these projects can fall in either of the thing. It is either, so we have not found any hybrid approach. It is important. So these projects, there is no hybrid approach. So it can happen that in the next 10-20 years we will find something there. So then it is either integrated or unified. Now, integrated is OpenCork. So if you see OpenCork's architecture, it's very complex, but it is kind of integration of many modules. That's why it is the integrated thing. Unified AIXI, so this is a unified framework, universal intelligence. Gato is also HTM based on basically on biological neuron. Now, Gato, HTM, AIXI, so these are all unified approach. Now, all these classifications are made high level. Projects in the same entry of the table still quite different in details. Yes, so we can't say that NARS is similar to AIXI. It's not. But they are under unified because the approach these two are taking is broadly a unified approach. But their approach to going to the AGI thing is different. Those two are different. So AIXI, NARS, so you can go through them. It's very nice. I mean, you'll like it. Now, if you go next.
Right, 1 minute.
Yes.
So AIXI is like this Marcus Hutter. Yeah. You want to go on?
No, I just wanted to say that AIXI is one of the most famous, I mean, unified approach towards intelligence. What do you think, Amritans? I mean, so you have, I mean, most of, I mean, technically everyone who is doing research in AI or AGI has heard about this architecture. So what do you think?
Yeah, so I will say that AIXI is like this amazing, like kind of model that Marcus Hutter has produced here. And Marcus Hutter is like a researcher in many areas, and he does include universal artificial intelligence. And approach he and other Shimduper Writer has taken are very different to the other modern but not so modern techniques in AI. It's like a top-down mathematical structure. Like he basically starts with the idea that, okay, let's write a mathematical definition of intelligence, okay, and then derive the properties of intelligent agent via proving mathematical theorems, okay. And other approaches are like bottom, they focus on defining agents that can solve problems in a narrow domain, and then look for ways to make them more general so that they can deal with previously unknown problems or problems in a different domain altogether. And the informal definition was proposed by Marcus Sutter and Sean Lake and Sean Lake is, I think, in DeepMind right now. The ability to achieve goals in a wide range of environment. This definition is very general enough that can be applied to non-human agents as well. Okay. And basically, this is the definition that they came up with. And the idea is like that overall definition and overall rewards that have been calculated. So basically, it learns via reinforcement, and its goal is to take actions that maximizes the total future reward provided by the environment. Okay. So in order to calculate this total future reward, it averages the reward over interaction history with the environment. The agent observes the environment, takes the action, and then the environment in turn generates an output and a reward. And this environment is basically unknown to AIXI. That's the whole point. This is something AIXI does not know. An agent has to take into consideration all possible environments AIXI has a bias towards simplicity. Of course, it tries to find a simpler model. And the interaction with simpler environments will have a bigger contribution toward agents' next action, as a matter of fact. Okay.
Yes.
And this is the whole idea. This is that the whole workflow that they are trying to show that, okay, there is some kind of a work that's happening, and AIXI is the model here. And you have these observation inputs and rewards input. And as you give some output, you will get some kind of reward, and then again, this whole thing kind of continues. So this is like a whole loop environment, also feeds back and comes with feedback and reward and everything. And basically, AIXI tries to learn and try to simplify and tries to gain, or like kind of try to build this mathematical model, which is gonna get the results back. Okay.
Yes.
All right. Now, this is something interesting, projective simulation. So I would like Kamal talk about this one.
Yeah. It's a very nice. I mean, so you saw AIXI. It's one way to approach university. Then there's projective simulation, which is being developed by Hans Briegel's group. Now, this is very interesting. Now, it's a framework of studying agency from a physical perspective. Now, see, PS agents learn from interaction with their environments, and their decision making is based on episodic memory. We all have episodic memory, right? I mean, our brain has that. Now, it is kind of taking a cue from the brain and then implementing that. So, inner workings of PS agents are based on random walks on graphs, which are set for a physical realization. Now, random walks on graphs. So there is this graphical neural network concept is coming, and or you can say knowledge graphs. It may be random walks we are taking, but something is connected. Like we all do that internally. Now, exciting feature of PS is the existence of a quantum version. Now, an agent that can, for example, exploit quantum effects to deliberate and learn more efficiently. Now, this is where a PS agent is a bit different from reinforcement learning engine. Although reinforcement learning is being tried in quantum domain, but PS agent actually has a quantum version. Now to exploit the quantum effects to deliberate and learn more efficiently. Now PS framework has been used to discuss deeper conceptual and philosophical questions as to what is mean to be an agent. Like so, PS agent. So although they are working, so their link is there. Hans Briegel's group. If you see their page, you will see this is very much similar to reinforcement learning, but it is not. I mean, overall, it may seem similar because there is an agent, there is an environment, and agent is interacting with the environment and all everything. But at a core level, it is a bit different from the reinforcement learning. Now, PS can be used as a model for reinforcement learning. As I said, it can be used as a model for reinforcement learning. Now, projective simulation, so this is how it happens. So there's an environment, there's a perception, there's a reward, and then there's action the agent is taking. So projective simulation is this, there's an agent here, and it is being taking the action based on the perception, and then it is maximizing the rewards and everything. It is similar. That's why I said, I mean, he said that it can be used as a reinforcement learning agent also, but it can be used in more wider aspects as well. Now, moving forward.
Interesting topic.
Yes.
Yeah, this is all in news these days, and so I think attention models came around 2014-15, and still the attention models have this problem. So see, the thing started with sequence to sequence. So they started putting RNNs on both sides, so LSTMs on both sides, encoder and decoder. But problem was you could not parallelize it. Okay, and then again attention mechanisms came, but again the common vectors you just could not parallelize. And but the news changed as transformers came. Now, of course, we are not going to go through the whole description what transformer is. I hope people watching this know, or they are willing to learn what transformer is. But the fundamental idea is this is a multi-layered attention, okay? And the idea is, as you will provide the data, and understand these are like regular neural networks. There are no special neural networks or layers that we are utilizing. And the good news is we could parallelize all of them. And again, it has an encoder layer, it has a decoder layer. Okay, so it is again following the encoding and decoding pattern. Now, guys, Transformer changed the game. So in 2017, I think I remember, Google published a very famous paper called "Attention is All You Need," and from that moment, I remember that transformers have taken the world of sequential data analysis, I guess, and NLP included, by storm.
Yes.
Okay. BERT came very soon. Google launched it, and then OpenAI started launching the GPT-1, GPT-2, GPT-3, GPT 3.5. Soon enough, I'm hearing GPT-4 might be launched. And we really felt compelled to put transformers there because earlier this was not the plan, but we were like, how can we not mention transformers now? Fundamentally, it's a deep learning model, okay, and it uses self attention, okay. Basically, it differentially weighs the significance of each part of input data, which is amazing. Like it is like trying to dictate or tell which portion or which context vector should get more weight, and this is very amazing. Like this is a human thing, like about so many things, like which part of the sentence should I focus more, right? You do not give same weightage to all parts of the sentence. And this helps you in understanding or taking inferences out really, really fast. So a transformer can be understood in terms of three components, okay? Encoder, okay, it has the encoding that encodes the input sequence into state of representation vector. Then attention, or better yet self-attention, okay? That transform or helps our transformer model to focus on right aspects of the sequential input stream. And then basically it is used repeatedly on both sides, encoder and decoder, okay? And then of course you have to have the decoder model that decodes the state information vector to generate target output sequences, okay? And of course, nowadays, like you can find diffusion models, and I hope people have seen ChatGPT recently. Okay, and diffusion models have been creating these amazing, like hyper realistic images of any text prompt that you provide. Right, it's just magnificent. And diffusion models again, like within last 2 years, have seen real good success at DALI 2 OpenAI models that have been available. Okay, and I think the other models are also Stability AI has also released quite a lot of models recently. And these are generative models. The idea is to basically generate these things. So diffusion is like they will keep adding gradual Gaussian noise and then go ahead and reverse. So we have shown you the GANs, VAE, that is variation autoencoder. And then we also have the flow-based models. But diffusion models have simply just taken world by storm. And the idea is again, these are neural networks which can be trained forward, backward. And similarly, based on diffusion models, and you might have seen these examples, that you can provide astronaut on a horse, and that is the imageless DALI 2 will generate for you. And every, like I think within few months or every quarter, we are seeing some brand new neural network, which is usually some kind, it is utilizing transformer models at the core, okay. And like very soon, very recently, we also saw like Codex example, right? Where you could generate a lot of code with simple text prompt. Then DALI 2 are there. ChatGPT recently launched, and again, OpenAI has launched this, and amazing language. It's amazing language model. I will still not say it is a complete AI model, but yeah, some responses are good. But yes, you can get deeper over there, and you can figure out in terms of causality where it might might be able to fail this. But these small steps that we are taking actually makes us really hopeful here. And these large language models, LLMs, as we have started to call them, are these artificial intelligent tools that can read, summarize, translate text, and even predict future words. So text generation, that is the exact task. And you can generate sentences similar to how humans talk and write. And this is like something that is almost already changing. People are using large language models in screenwriting, like they are writing how the story will develop, right? Some people have started developing some small blogs or news articles just based on this. Although there would be a negative downside here, it could be used also to spread fake news. You could just populate like, and this is why Stack Overflow basically banned ChatGPT answers. You could just start manufacturing answers around any question and just putting it there, right? So all of those answers are again totally banned. So yes, this is state of the art. This is really recent, and that's why we felt compelled to put it there. But again, you need to be careful here. It is still just solving at a very large scale, and the companies that are working with, they do have like almost all the internet data, and they are using reinforcement learning, but it's still very hard to tell how much of it is will actually translate to something meaningful in long run, or is it just gonna be a gimmick? 1 year it will work and then people will forget about it. I have no idea, because there is a result that I have seen. It is impressive to build with simple prompts. You can get impressive results. You just go a little complex. Nah, the results are not very convincing. Okay. But you never know. Maybe progressively it will just reach over there. That's my hope. Meta learning. This is a word like that's thrown around a lot. So, Tamal, can you tell us what is meta learning?
Yes. Yes, meta learning is quite interesting, and we know machine learning, we know deep learning. Now let's come to meta learning. Now, meta learning is not a single discipline. We should make it very clear. It's not a single discipline. It's rather different types of methods that can capture knowledge from learning algorithms. It's a most active area of research in the deep learning space, and there's a school of thoughts within some school of thoughts within AI community subscribe to the thesis that meta learning is one of the stepping stones towards unlocking AGI. Now, the reason being why they think so is because it's not a single, it's a combination of, I mean, it's like a different approach, different types of methods that can capture knowledge from learning algorithms. So it is like a different ways you can capture knowledge, like a human brain works. Now, in context of AI systems, meta learning can simply be defined as the ability to acquire knowledge versatility, and as humans we are capable to acquire multitasks, we are capable to acquire multiple tasks simultaneously with minimum information. Now, in our day-to-day work, I mean, so if you are working somewhere, you'll know that sometimes you have to multitask. So someone will give some task, some other will give some task. Now you have to parallelly work, either parallelly or
Yeah.
you have to combine something. Now, so all these things will become meaningless. Sometimes you say that, okay, fine, someone gave you task, you might have done something similar, may not be exactly the same, but something similar. And you say that, okay, fine, I did something similar, I can take this and I can do this task. Now, this is how you simultaneously learn, and with minimum effort you can actually solve the problem. Now this is where this is what meta learning is. Now it is like we can recognize new type of object by a single picture. So we can multitask activities such as driving, piloting, all these things. So while AI agents can master really concepts, they require massive amounts of training on an atomic subtask, like learn how to learn. Now this
Mm.
is an important line. So there are courses, there are, I mean, uh, things you can learn about learning how to learn. Like, so this is a path of versatility, requires AI agents to learn how to learn. Now, how an AI agent can multitask and how it is going to take different tasks and solve it. So this is what meta learning is. Now, moving on.
One, sorry.
Now, yes. Now, meta learning, a good machine learning model often requires training with large number of samples. We have seen that resource and compute power is one of the key challenges here in machine learning and deep learning community, which is hampering, I mean, which is kind of a hindrance. Like you cannot have an unlimited number of resource supply to train unlimited number of data and all everything. That's why we sometimes have to break the data into chunks and analyze it based on that. Now, humans learn new concepts and skills much faster and more efficiently. Kids who have seen cats and birds only few times can quickly tell them apart. Now, this is a classic example of how we grow as a baby. Now, our parents usually point us to, okay, this is. Sometimes we see them, sometimes we understand by just by observing someone, some adults. A baby can know what he's talking about or what is the objects behind it. Everything. It's a square, circle, rectangle, bird, fly, buildings, all these things. Well, with minimum effort, we are able to learn. Now, this is where meta learning model comes into the picture. Now, we expect a good meta learning model capable of adapting and generalizing new tasks. Generalization is one of the areas where deep learning is lacking. Like there are models which don't generalize. Generalization problem is a very inherent problem of deep learning models. Now, we are hoping that meta learning will solve that thing. Whereby the approach is like that. So we are hoping that it will solve the generalization problem of deep learning. Now, the tasks that can be well-defined family of machine learning problems, supervised reinforcement learning, etc. Here are a couple of concrete meta learning examples. Now, a classifier trained on non-cat images can tell whether a given image contains cat after seeing a handful of cat pictures. Game bot is able to quickly master a new game. A mini robot completes a desired task on an uphill surface during test, even though it has only trained in a flat surface environment. Now, we are hoping like that. So these are classic examples of meta learning. Now, when you move on, now, there are different types of meta learning models. Now, humans learn following different methodology tailored to specific circumstances. We learn based on the problem in hand. In the same way, not all meta learning models follow the same techniques. Some meta learning models are focused on optimizing neural network structures, while others focused on finding the right data sets to train specific models. Now, this is very interesting. A research from UC Berkeley, comprehensive job enumerating different types of meta learning model. Now, UC Berkeley has done this job, like, I mean, categorize what are the different types of meta learning models. Now, first one, few source meta learning. Now, idea of few source meta learning is to create a deep neural network that can learn from minimalistic data sets, mimicking, for instance, how babies can learn to identify objects by seeing only a picture or two. Now, this is a technical memory augmented neural networks or one-shot generative models. Like you see a picture once, then you memorize it, then you don't have, then after some time, if I ask the neural network, so just by seeing the neural, the image once, it is able to classify the image. This is few shots learning. Then optimizer meta learning is are focused on learning how to optimize a neural network to better accomplish a task. Now, those models typically include neural networks that apply different optimization to hyperparameters of neural network in order to improve a target task. Now, here the evolutionary algorithms or genetic algorithms will come into the picture. So this is how those algorithms, genetic algorithms, so evolutionary or differential evolution, all these algorithms are there that can optimize the neural network, optimize a certain task. Those are optimization algorithms. Now, if you train them carefully, they will be able to achieve the desired tasks. Now, moving on. Then there is metric meta learning. Now, the objective of metric meta learning is to determine a metric space in which learning is particularly efficient. Now, this approach can be seen as a subset of few source meta learning in which you learned, in which you use a learned metric space to evaluate quality of learning with a few examples. Now, this is metric. Now, this metric is, it is able to identify the space in which the learning is efficient. Now, we sometimes do that. We sometimes find the way we learn. How do we optimize our learning, our own? Now, we sometimes see that, okay, fine. We'll approach these things first. We'll do this first. We'll break the entire chapter into segments and then we'll learn. So this is like finding how to best learn a given chapter or how to best do a particular task. Then there is called recurrent model meta learning, which is very similar
Can
to
I
what
ask a
Arden
question?
model is.
Hey, Tamal,
Yes.
can I ask a question?
Yes. Yeah.
Hey, so the question I am having here exactly is, this metric meta learning,
Yes.
would this be any different from, let's say, the optimizer meta learning? Like, what is the major difference here? Because I'm just thinking like, how could I could differentiate them?
Yes, it's a very good question. Like optimizer meta learning and then metric meta learning. Now, what optimizer meta learning is basically you have a neural network which is trained to do something. Now, what optimizer meta learning will do, it will try to basically optimize that neural network based on certain hyperparameters, based on certain criteria. What the way we do, like learning rate or whatever hyperparameter we'll choose while you train that neural network. So optimizer meta learning will basically optimize that neural network so that it can actually produce the given task more efficiently. Now, metric meta learning is like it will determine a metric space in which the learning is particularly efficient. Now, it will look for that. So it is, you can say this is a subset of few source meta learning.
Okay.
Like, yes, like what you can say is metric. So what I mean by space is like, say, for example, you are giving certain pictures. Okay, now cat. So there are various kinds of pictures available for a cat. Some may be clear, some may be hazy, some may be cat is very far away. Some cats may look like a furry dog. Okay, so there. So you will give. So what metric meta learning will do? So it will. So if you give those kind of pictures where the cat is kind of hazy, something, and then you say, okay, these are cats. So what it will happen is that particular model, even though will train your model, say 90% of the data will be a clear picture of clear images of cat, but there will be few pictures which will throw in, which will be a bit difficult to classify. Now, what metric meta learning will do? So it will actually go, it will try to see those pictures and then try to learn. So it will be a more efficient algorithm. It will be. So it will have known defined kinds of pictures of a cat. Then it will be very easy for that algorithm to classify an image, a random image you pick and you say that neural, okay, what is this? Then it will analyze and they'll say, okay, it is a cat. Just because it has seen quite a number of pictures earlier of various kinds of cat pictures, so it was able to efficiently tell, okay, this is a cat. If it had not, then it would have said something else, like a dog or something.
Agreed.
So it is just a subset. You can say metric meta learning is a subset of few source meta learning. The first one we discussed.
Yeah, of course.
So, yeah.
I think we can continue then.
Yeah. So it's clear, right? I
Yeah,
mean,
of course.
yeah. So, okay, next and the last one is recurrent model meta learning, which is, you can say from the name, is based on RNN model. RNN or LSTM, you can say. It's a type of meta learner tailored to RNN, such as LSTM. In this architecture, meta learner algorithm will train an RNN model, which will process the data sequentially, because RNN is a sequence to sequence model. And then it processes new inputs from the task. In image classification setting, this might prove passing in a set of image and label pairs of a data set sequentially. So meta reinforcement learning is something which is being developed now. So that falls under the classic category of recurrent meta learning. Now, importance of meta learning is steadily increasing in deep learning. It transitions more towards unsupervised models. Now, if we can generalize the process of learning to learn new tasks, the idea of AGI suddenly becomes more pragmatic. Now, when you say an AGI, we definitely mean the way our agent will learn like a human being. Now, we human beings are good at learning because we learn from all kinds of things, as by observing, seeing, hearing, all these things. So this is like our brain is generalized for those things. Now, but for an agent, AI agent, to able to learn, we need to specifically tell, okay, learn like this, that, and all everything. It cannot learn like in general. So
Yeah.
so a classic example is, if an algorithm is trained on cats and dogs, cannot differentiate between a bus and a car. So it's like that. That's why transfer learning, all this continual learning comes into the picture. Episodic memory, which we just introduced, all
Yeah,
these things,
absolutely.
so that it can generalize. Now, once we have a meta learning models, if this section or this track of research gets successful, all of a sudden AGI will be realizable. So it's just that how you learn something more in a general way is what's target of meta learning models are. So it's a very
Absolutely.
good research. I mean, you can follow the research around. It's very good.
Yeah.
So yeah. So moving on. Yep.
STU.
So yes. So Amrita, I know ever since we met, you are very, I mean, kind of fascinated towards HTM Numenta. So
Yeah.
can you explain a bit more on HTM?
Yeah. So see, the idea has come through the understanding of neurons. Okay. Fundamentally, it's not something that so they have tried to understand. It's like a feed forward input from the input space. So basically, I think Jeff Hawkins tells this, that basically he was just touching the cup, and immediately like it clicked to him that even if he's just touching the cup, like he can kind of predict like what is going to come at, or where is the handle and all that. Like he could predict all this. And
Hmm.
basically, by study of the brain, they have figured out there seems to be series of these neurons. Okay, the series of neurons, like column-like neurons. Okay, column-like neurons structure that actually have been proven that they actually exist. Now, of course, our trouble is like how do we come up with that mathematical model? So these are called basal synapses, that these kind of receive contextual input from the nearby cells in the same region and recognize patterns that precedes the firing of the cell, like what come and why it is coming from there, right? And these kind of depolarize the cell, contribution to action potential, but they are not large enough to generate an action potential as proximal synapses. They just behave like a small prediction mechanism for the next feed forward one. And then we have apical synapses, which are like top down. So from cells in higher layer and depolarize a cell in basal synapses. Okay. And these multiple times when they come together one by one, column by column, step by step, it almost looks like the context is being carried through. The context is being carried through. And this is what we are
Yes.
trying to show you here in this diagram. And this research, Numenta is like very pioneers in this, and they are almost taking a brain. They try to understand what brain is doing. They have like a lot of neuroscientists working over there, and they try to understand that how these co-activation of synapses contribute to action potential and how these are connected at the end of the day. Okay, and this
Yes.
has really changed the game. And still, okay, I will not say that uh, very few applications have been found, but still they are working very. And the idea is that again, the idea is like similar to like a convolutional neural network. You start to detect simple features, and then you keep adding, keep on adding them. And the idea is
Yes.
this thousand brains, like what the theory by Jeff Hawkins that has been given, that a lot of these parallel processes are working rather than learning just one model's thousand brain theory of intelligence says that every part of neurocortex, which is the biggest area, learns complete model of objects and concepts. Okay. And long range connections are made in neocortex that allows models to work together. and which actually creates a perception of the world. So you can understand some area will be like limited for your hearing, and some area might be limited to your vision, right? Actually, there is a phenomenon, and it is called phantom limb. Have you heard about it?
Yes, phantom
So
limb.
phantom
Yes.
limb is like if someone's body part is accidentally cut off or chopped off. People have felt, and it's like, okay, so your brain has a certain area, let's say registered to that limb. Okay. So let's say even if the limb is chopped off automatically in a, let's say, some brutal accident, many times your brain feels that because that area is still very dedicated to that limb itself, that the limb is right there. The limb is not actually there, but your brain is actually feeling it. Over the period of the time, rewiring actually happens. But initially, you will feel that there is some noise, or you will feel some sensation almost at the cut. Okay, it as it like the limb is actually there. It's not, it's just your brain is playing tricks at the end of the day. But this is more biological, it is more inspired by heavier learning, and it's fairly online learning and unsupervised. And this is why people are very excited about this. Okay. And the idea is again, very small amount of data would be required. So I will encourage everyone to look into Numenta's research and look into thousand brains theory of intelligence. This is an amazing idea. Still,
Yes.
like we need to find some more success here, but I think we are kind of going in that. And these neocortical pyramidal neurons, these are your biological neurons. And again, the idea is basically they are all working together, creating these models. Okay. And STM models inherently is like, again, dealing with thousands of synapses. And the idea is active dendrites will recognize hundreds of unique patterns. And basically they call connect with NMDS strikes. Okay. And uh, kind of having this common set of synapses. And basically they learn by modeling the growth of new synapses. So as the new synapses are growing, they try to learn the model of that world or that object. Okay.
Yeah, that's
So
good.
this is again like very interesting, explainable AI. So what do you have to say about this, Tamal?
Yes, yes. Now, explainable AI with knowledge graphs. So now, explainable AI is a field which came when there are quite a few international incidents happen with our data, which the data breaches happen where personal data got exposed and everything. And that is one. Second is we don't know how the AI produce that output. We use it in our decision making, business decisions. I mean, at a corporate level, at a very high level, senior management level, we use those. All the models are productionized, so they are being used in real time decision making in banks, in laws. I mean, in law firms, banks, and other government agencies and all. But we really don't know how
Hmm.
or why that decision was made by the neural network, why that output. Now then all these things came into I mean came together, and the field of explainable AI was born. Now explainable AI with knowledge graphs, as I said, graph neural networks, knowledge graphs, these are key in understanding how you actually derive at something, some answer. So if there's a question, how to derive at the answer, we take sequence of steps. Explainable AI with knowledge graph, two of the most powerful things. You can combine these things. Knowledge graphs and graph neural networks are being used to do explainable AI. Now, explainable AI is basically trying to understand the black box nature of the deep learning or machine learning models. Now, we try to unbox the box, as you said. Yeah, so unboxing the box, it's basically that. So that we know why the decision was made. So there are quite a few literatures available. You can go through it. Now, what we can say here is explainable with knowledge graph on integration of semantic technology symbolic systems. We introduced neurosymbolic AI earlier. Now, when you combine the two, which get more comprehensible AI. Now, deep learning model contributed to reaching unprecedented results in AI. We don't, but they don't provide human level understanding explanations of their predictions are achieved. As I said, we don't know why that action was taken. Now, novel neural network architecture may be designed to natively encode explanations. Some recent approaches have captured better model hierarchical relationship causality mechanisms are promising. But this thing, I mean, why we have introduced this is because if you want to have, if you want to get to an AGI agent, we should be looking at these things. Like the agent should be able to explain. At least we should be able to understand why that agent took that action
Right.
or that decision. Hence, the integration of explainable AI in AGI is important. Hence, we introduce the concept through knowledge graphs, and graph neural networks is there, which is similar concept. So when you combine these two, you'll get an agent which will have everything. Now, different approaches for creating AGI. Now, we have seen earlier, like some of the research tracks which we combined in that matrix form, where all the projects are being categorized. Now, this is a broad approaches to creating an AGI. Now, we don't have clear understanding how to achieve an AGI or a human level. There are debates happening all over in Twitter, in blogs, in everywhere. So these are some of the broad approaches. One, networks of various weights filter combined. So this is basically an example of artificial neural network, the one we do, feed forward propagation and everything. Next, inference engine, generic inferencing algorithms on data represented as relationships. Next, generation of new entities through exploration techniques and fitness function, which is the genetic algorithm, which is one of the optimization algorithms. Next, technique based on finite state machines and memory queries like semantic search or finite state machines. So we don't think. So as the same question, we don't think one approach will be enough. We have to see a combination of the approach. What do you think, Amrita? Here.
Yeah. So this has been like very hot debate, like how we are going forward, and there are connectivities like the blank slate approach versus hybrid approach,
Yes.
like that has been going on for quite some time. And of course, I do not know the right answer here either, but I think
Yes.
something like neurosymbolic AI does seem very promising to me. I'm also like very interested in looking into these third generations of artificial neural network, the spiking ones that we have discussed
Spiking
actually a
ones.
little bit. Yeah.
Yes.
So I am thinking like we have to go towards the hardware and the software, both of them at the same time. Because even I can make
Neuromorphic.
the argument if the hardware is also not suited enough actually, because you have a memory and processing separation in the modern ones, and the human brain is definitely where memory and computations are very much overlapping. So it is slightly hard to say which model to take, but I am very much in favor of taking a hybrid approach here to build this high level intelligence. Okay.
Yes.
And again, you have these multiple approaches where you have human-centric model of human intelligence, and then you have science models of reality, causality, and mentality. And most of the time, of course, we have these human-centric models which are just reigning everywhere. And I think this is amazing that the way we have progressed, like thinking from metaphysics, logics, mathematics, science, computing, cybernetics, ANN, like artificial neural networks, then we think symbolic, logical, general AI, machine learning, deep learning, and that again translates to weak narrow AI, neurosymbolic, general human level intelligence, artificial superintelligence, transdisciplinary AI. And again, you can have a man-machine hyperintelligence where you have merged and everything, fused everything together, right? And Stuart research says that most of the time, whatever we read in media, like that's 80% wrong. Like most of it is highly blown out of proportion. And this is not something that has happened. And but yes, we need to be patient enough. We need to be patient enough what we are building. We need to believe in the long-term goal. We need to believe in long-term goals here. And these are some
Yes.
few researchers that we have been following: Dr. Ben Gödel,
Yes.
Dr. Pei Wong, Ere Orkazil, Marcus Sutter, Joshua Tannenbaum, Jürgen Schimmelberg. And these are just few people. Like again, if you just start searching, you could definitely find few more people who are working. And I think now we might also have to add Jan LeCun's and Geoffrey Hinton as well, because they also keep coming up with some ideas around how you will build universal intelligence, right? But again, this list is never ending, and we also like to contribute, me and Tamal and any prospective
Yes.
viewers that they are interested. And for this, we are announcing that we are going to be called Neurocortex AI, and this would be a community, collaborative learning community without any specific teacher. And the idea of that, we are removing or replacing the idea of teachers with lesser senior researchers or developers who will act as mentors, and we will direct new students along a learning roadmap made of online courses and research paper. So please understand, this is not like a coaching class that's going to start. This is self-study. Okay, very much self-study.
Yes.
There would be a little bit of guidance, and you can see that we have researched and worked on more than, at least the 40 is like minimal number. Okay, of course, you can read hundreds of papers, but 40 research papers to understand in-depth algorithms in spanning across machine learning, deep learning, reinforcement learning. Okay. And then, of course, you need to go deeper with, let's say, machine learning, deep learning, Bayesian networks, hidden Markov models, generative adversarial networks, reinforcement learning, such as Q learning, temporal TD learning, that's temporal difference learning. And again, we could also focus on some aspects like computer vision, robotics, speech recognition, natural language processing. Okay. And we have been doing this under a different name called RLA, but we are again thinking to kick it off, and we are changing the name here to neurocortex.ai. And again, some of our research areas, which I think me and Tamal can confer that this is what we are looking. And of course, guys, please understand, we are looking into solving the problem of general intelligence. And one of the first thing that we would like to make it clear that, again, we don't know the answer. So please do not say that we already have the idea. No, unfortunately not. But we will be geared toward AGI and third generation of spiking neural networks. And we will try to understand the latest state of the art. And this is why paper reading is such an important concept, to see how they are going towards AGI. And also, so Tamal has some experience, and
Yes.
even I'm learning quantum machine learning. And we will be very happy to guide you how quantum computing will add an advantage and working on hybrid quantum classical neural networks. Okay. One aim would be to publish research papers, articles, blogs about our research, even make YouTube videos. If we can make explainable videos, we'll love to do it on the same channel. Okay. And we would mentor new AI researchers to enhance research capabilities of the whole group as well as the individual. And at the end of the day, I think my goal here is to build an end-to-end framework for the research and experimentation around AGI. And I think that's what we are at. And there would be a last video where we would try to conclude everything. But I think this has been an interesting journey. This video would be the last video for this year. The last video will come out in the brand new year, hopefully. So I guess that's all from my side. And this is a discussion that will continue because there would be new architectures. Okay. This is not something we are concluding completely. But this is, I think, pretty good introduction in so many novel architectures that we have across right now. Okay.
Yeah.
That's all, guys. Thank you so much. And
thank you.
Wish you all a very happy new year and a Merry New Year.
Happy New Year, everyone.
Christmas. Okay. And
Merry
thank
Christmas,
you, Tamal.
Happy
Thank
New
you
Year.
so much.
Yeah. Thank you, Amritans. Thank you.
Okay.
See you. Bye.
Bye, guys. Take care.
Bye. Bye. Take care.